Welcome to The Explainer. Today, we're going to tackle organic chemistry. And here's the thing. It's the science that builds pretty much everything around us, from our DNA to the plastics we use. But it's not about memorizing a bunch of random facts. It's actually more like learning a logical language, a set of rules for how our world gets built. So let's kick things off with a little puzzle. Think about it for a second. What do a plastic bottle, a life-saving medicine, and, well, you all have in common? And the answer is carbon. Yep, one single incredibly versatile element. It is the ultimate builder, the absolute backbone of life, and the foundation for so many of the materials that define our modern world. Okay, so here's how we're going to break this all down. First up, we'll look at why carbon is such an amazing builder. Then we'll see how chemists actually draw these things. After that, we get to the fun part, making and breaking bonds. Then we'll talk about the chemist's cleanup, and finally, how we figure out what we've actually made. All right, first things first. If we want to get a handle on organic chemistry, we've got to understand the star of the show, the carbon atom itself. What is it that makes this thing so special, so good at building? Well, the secret sauce is something called covalent bonding. See, instead of giving away or stealing electrons like some other elements, carbon is a great sharer. And this sharing creates these incredibly strong, stable connections. It's kind of like Lego blocks clicking together, you know? It allows carbon to link up into these massive, complex chains and rings. But here's where the real magic comes in. Carbon is a molecular shapeshifter. Through a process called hybridization, it can actually change its geometry. It can form 4 single bonds to make a 3D pyramid shape, or it can form 3 bonds and be totally flat. It can even form 2 bonds and be a perfectly straight line. This flexibility is everything. It's the key to carbon's amazing versatility. Now, these connections come in 2 main flavors. Every bond starts with a super strong direct link called a sigma bond. That's the backbone. But if atoms want to get even closer, they can add these weaker side-by-side connections called pi bonds. So a double bond is just 1 sigma and 1 pi. A triple bond? 1 sigma and 2 pi bonds. And because those pi bonds are kind of out there and exposed, that's usually where the most interesting chemical reactions happen. So we get how carbon bonds, but some of these molecules are gigantic. We're talking millions of atoms. So how on earth do chemists draw these things in a way that actually makes sense to anybody? Well, they focus on the important parts, the parts that actually do stuff. These are called functional groups. Let's go back to our Lego analogy. If the carbon chain is just a bunch of basic bricks, the functional group is that one special piece, like a wheel or a propeller. It's what gives the whole structure its unique character and determines how it's going to react. And to make sure everyone's speaking the same language, there's an official rule book for naming everything. It's called the IUPAC system. And really, it just ensures that one specific name always refers to one and only one structure. No confusion whether you're in a lab in Tokyo or Toronto. Okay, now we get to the action. Because chemistry isn't just about the molecules that exist, it's about change. It's about that dynamic process of taking the Legos apart and rearranging them by making and breaking bonds. So when a bond snaps, it can happen in 2 main ways. You can have a fair split, which is called homolytic cleavage. Each atom walks away with 1 electron. Very civil. Or you can have the unfair split, heterolytic cleavage. That's where one greedy atom takes both electrons, leaving the other one with nothing. And that unfair split creates 2 very different players. The atom that took both electrons is now what we call a nucleophile. It's rich in electrons and it's looking for a positive charge to connect with. And the atom that lost its electron, that's an electrophile. It's electron poor and is desperately seeking a negative charge. And these 2 players, the electron seekers and the electron donors, are at the heart of the 4 main types of chemical reactions. They can swap partners in a substitution, join together in an addition, break off a piece in an elimination, or simply shuffle their own structure in a rearrangement. So after you run a reaction, the flask isn't this pristine container with just your new molecule in it. No way. It's a messy soup of leftovers, byproducts, and the thing you actually wanted to make. So the next critical step for any chemist is the cleanup. And the absolute gold standard for this cleanup is a technique called chromatography. The best way to think about it is like a molecular race. By getting all the different components in the mixture to move at different speeds, chemists can separate them out with incredible precision. Now, this works in a couple of ways. Adsorption chromatography is all about stickiness. You run your mixture over a surface, and the stickiest molecules lag behind. Then there's partition chromatography, which is all about solubility. It separates things based on how much they like to dissolve in a moving liquid versus a stationary one. Okay, so you've made your molecule, and you've managed to purify it. You have this beautiful, clear, pure substance. But how do you know for sure what it is? How do you figure out its exact elemental recipe? For this, chemists turn to quantitative analysis. They have this whole toolkit of clever tests to measure the exact percentage of each element. For instance, they can literally burn the sample and measure the CO2 and water produced to figure out the exact amount of carbon and hydrogen. And there are similar specific tests to nail down the amounts of nitrogen, sulfur, and other elements. But what about oxygen? Turns out, oxygen can be a real pain to measure directly. So chemists use this brilliant little trick. They measure every other element precisely, add up all those percentages, and then just subtract that total from 100. Whatever's left over, well, that's got to be the oxygen. So, you see, from bonding shapes and a universal naming language, all the way to predictable reactions and purification, organic chemistry isn't chaos. It's a logical system of rules that governs our universe's master builder, carbon. And that leaves us with a final thought to chew on. We've just explored the language of carbon. What secret languages do other elements speak?